Hello everyone, welcome to the numerical methods class. In this class we will be talking about numerical differentiation and integration, basically the introduction of these, and this is called chapter 19. And after this, in chapter 20, we will talk about the engineering applications of the numerical differentiation and integration, and then in chapter 21 we will go to the actual numerical methods used for numerical integration. So in this chapter we will be just introducing these terms. How do we use them basically manually, let's say. Then in the later chapters we will go through the numerical methods. Let's start with the introduction to differentiation. And as you know, differentiation is also called the derivative actually, and it is calculated by a difference approximation. You know, we learned about this before, and this is just the difference approximation, as you can see here. And if we say that the delta x is allowed to approach 0, here, this one, then we can take a limit of it which approaches to 0. Then the difference approximation in this scenario becomes a derivative shown by dy divided by dx. It's the derivative of y function with respect to the x input, for example. So here you can see some pictures about how the derivative work. Here you can see a function, and the derivative actually is given as the tangent at one point. And here, because we have a finite difference approximation, you can see here, it's just a difference between xi point and xi plus delta xi point. So it's just a linear direction between these points, this one. And delta y is here, and delta x is here. So delta y divided by delta x is equivalent to fxi plus 1, this one, minus fxi. This value is delta y, the top part. And the bottom part here is delta x, and it is basically xi plus delta x minus xi, which gives delta x to us. So from here, you can see also delta y and delta x in a different point, like this. It can change in each direction because the tangent is changing. But in actual, if we take the delta x to 0, so we are minimizing it. Actually, you can see here, this is larger, this is smaller, so this is getting closer to the tangent. And when we have 0 delta x, then it becomes directly the tangent direction. So it becomes the derivative of the function. And the second derivative, so this was the first derivative, first of all, and the second derivative tells us how fast the slope is changing. So the first derivative is the slope or the tangent, and the second derivative shows how fast it is changing, and it is given by this d square y divided by dx square. So we have two derivatives, and it's commonly referred to as the curvature, because a high value for the second derivative means high curvature. So that gives us an information about the change of the slope. Partial differentiation is another term that we are going to define, and it is also called partial derivative, and it is used for functions which has more than one variable. So basically, in the previous slide, we had only one input, which is x, or variable x, and the derivative was taken with respect to x. But in here we have more than one variables, like x and y, for instance. So the partial derivative is the derivative of the function for one variable while the others remain constant. For example, let's say we have a function of f with two variables, x and y, and the derivative with respect to x is given as del f divided by del x. Now this is shown a different d, actually you can see here, because it represents the partial derivative. That means we are only taking derivative with respect to x, and we take the delta x limit to 0. Also, we can take the derivative with respect to y, which is the second variable, like this. And in that scenario, we will take delta y, as you can see here, and we will take the delta y to 0 in the limit to get the differentiation. So to get an intuitive grasp of partial derivatives, recognize that a function that depends on two variables is a surface rather than a curve. So when we have only one variable, x, for the function, then that's a curve. But when we have two variables, then that becomes a surface actually. And also suppose you are mountain climbing and have access to the function f that yields elevation as a function of longitude, the east-west oriented x-axis for instance, and the latitude, the north-south oriented y-axis. So you are climbing to a mountain, and the function, so you can define the function of the surface of the mountain as x and y axis. So these are two variables. And if you stop at a particular point, x0, y0, the slope to the east would be, so east means this x1, so we take the derivative with respect to x, and this becomes the slope to the east. And the slope to the north, which is shown by y, the north-south oriented axis, then it is a derivative with respect to delta y. So these are taken as the partial derivatives. In this slide, we will talk about integration. And integration is actually a reverse process of differentiation. And the integral of a function fx is given by the fx dx in between two ranges, the minimum and maximum values. And this fx function is called the integrand. And the integral means the total value or summation. This shows actually a total value or summation of fx dx over the range x equals a to b. The range is this. And the integral of fx corresponds to the area under the curve of fx between x equals a and b. Here you can see that a and b are the limits, and this is the function. So we simply sum all the area underneath this function between a and b to take the integral of the data. So it basically shows us the area under a function. When we compare differentiation and integration, basically differentiation means the slope of the function at a certain point, and integration is the area under the function between a range. So these are the differences, and we can use them. For example, in dynamics class, you already learned to calculate the velocity using the position function. So from the position or the location of the particle or an object, when you take the derivative of it, you will get the velocity. So this is, let's say, the position function, and you want to take the derivative at this point of the function to take the value of the velocity. So differentiation gives the velocity for the position function. So we said that integration is the reverse process of it. Then when we have the velocity function, we can get the change of the position by taking the integral of this function, and we go reverse in that scenario. So this is the velocity function, which is this, and we take the area underneath to get the delta position, delta y. So from 0 to 4, actually, or 0 to 6 seconds, it takes this much position or location, movement, let's say. So it goes to here. Then, in general, integral evaluation is I is given as fx dx in between two ranges, and it gives us an area, so that means it gives us a change of the value that we want to find. And it equals to solving differential equation dy dx equals fx actually. And dy dx is, for example, here is the velocity. For yb, given the initial condition ya equals 0. So this is kind of the differential equation we define based on this integral evaluation. In this slide, we will be talking about the function types that we are going to use the differentiation and integration. And we can define the function types in three forms. The first one is the simple functions, simple continuous functions. These are easy to differentiate and integrate analytically, such as the polynomials, exponentials, trigonometric functions, and you learned about these analytical solutions in your calculus classes. And the second one is complicated continuous functions, and these are difficult or impossible to differentiate or integrate analytically. That's why for these especially we use numerical differentiation or integration. And the third one is tabulated functions, which means that we have a data actually rather than a function. So we have values of x's and fx values, the outputs and inputs, given at a number of discrete points. And we can use these in the numerical integration and differentiation to be able to get the integral or the derivative of the tabulated function, let's say. And it is usually the case with the experimental or field data, and in engineering especially, we are dealing with this kind of tabulated functions because we will have some experiments or some measurements, and this will be important for us to be able to use the integration and differentiation using numerical methods.